Okay, so I think we can start. We're very happy to have Cliff Nick here talking to us about H2O, which I don't know much yet about it, but so far it seems to be an amazing framework. So please go ahead.
Thank you. Okay, I'm Cliff Nick. I guess some people know who I am. So I've been playing around the programming world for a long time. I guess sort of the major thing that I did was I did the JIT, the original high-performance JIT hotspot, against a whole lot of naysayers who said it couldn't be done. And basically changed how the world thinks about JITting code now. No new language comes on the scene without some sort of plan for JITting. I've worked on hotspot for more than 15 years in different places, and I decided it was time to change. So I'm doing something completely different now. I'm using Java instead of implementing Java. So I'm implementing this open source thing called H2O, water. Been implementing it for the last several years. It's a tool for doing machine learning at scale on big data. And it is one of the fastest ML tools out there. And it's implementing the best of breed machine learning algorithms with all the bells and whistles, with all the right stuff. And it's a strong focus on what data scientists actually need and use and enterprise level quality, tightly integrated into other programming languages people typically use to do machine learning. And it's all about doing cluster computing on big distributed data sets. And that's what this talk is not about. This talk is really about how we implement these algorithms. And I am not a mathematician. I've kind of, handed and grown myself over the last several years and becoming sort of reasonably, good there, but it's not my expertise. Instead, this is a low-level hacker talk, low-level systems engineering talk. I'm going to talk about clusters and high-performance computing, memory bandwidth, fork join, distributed parallel execution, happens before relationships, distributed KV stores, and things like that. And the reason I'm going to do this talk is really I'm looking for some other people who are interested in this kind of tool building. I'm building a tool, and I need somebody who's got a really strong engineering head, and maybe they're comfortable with Java. That's not a requirement. We in fact picked up Matt Dow, who's got a data.table. If in our community, data.table is a really high performance way to do all kinds of interesting operations on large data sets in R. He's a total C hacker head. We've got doing the same thing at H2O, Java, and doing it distributed in parallel. So that's kind of exciting. So we can take old school C hacker heads and get them, teach them to use Java, and actually have them code run faster. Okay, so what does H2O do? So I'm going to talk about what it does, because I'm going to use that as a foil, as a reason to explain what things I have to do to make it do these things. So it's anything you want to do on big 2D tables is the general rule. Mostly Java, that's going to read or write a row of data, which will generally be an observation of a data set. There's maybe some nearby rows for stencil calculation, and/or computer reduction, produce some results out. The speed is typically your data volume divided by your memory bandwidth, which will vary by hardware, maybe 50 gigs a second. The data is therefore highly compressed always because it's faster than memory bandwidth. And we do things with numbers and times and strings in our math. That's sort of the limit of what the kind of data looks like. The width of these tables, let's say 2D, the width is, 1,000 columns is fast. It's blink fast. 10,000 columns works pretty well. 100,000 columns, the loops just start to be parallelized the wrong way. It still works, but it's getting slower. But the length, we have tested it at trillions of rows. We've done a logistic regression on about 10 trillion rows on 100 EC2 node, 100 node cluster EC2, and it took a minute and a half, something like that. So this is like insanely huge sets of data running on a commodity pizza box x86 hardware runs really well. Okay. So I'm going to talk a little bit now about what kind of code that people end up writing, and then we'll get into what implementation takes to make that work. So most simple Java just works. And it's mostly done with this very clean implementation of map and reduce paradigm. It's not the Hadoop map reduce. It's a theoretically clean map from type A to type B, reductionist, take two B's and make one kind of thing. It's fast. It's parallel, distributed always. The reads run at the same kind of speeds as the Java array load. Writes go a little bit slower because you have to do a compression step along the way. But we're using memory bandwidth limited anyhow. And we also implement the entire Java memory model semantics always, even on the distributed cluster. So it's exact semantics. We'll get more on that in a minute here. So take a quick look at how we distribute the data, and then how we distribute the compute. So, how does it work, data? So the data is kept in vectors, arrays, giant distributed arrays, whose length is longer than what you can have in an int. So the indices are 64 bits. There's an add and a set call to fetch and set data. There's a notion the missing element is an A. That's a data science specific thing. It's not necessarily an engineer's idea, but the mathematicians love it. And of course, you can pin. The data sets are variable size. You can change things on the fly. In fact, you can do parallel distributed pins, and I'll do order preserving pins as I go. So let's show you how that's done in some point here. So it's a big vector. It's very long, as I mentioned. It's compressed. It's conceptually full of Java primitives, generally double, but it's due to compression. It's not actually implemented or represented in memory as a Java double. There's something else happening with compression. Random access is completely supported. However, you're guaranteed that if you do stride one linear access through the data set, you'll get memory bandwidth speed. So that's sort of the cost model. And all throughout this talk, I'll keep mentioning how I'm implementing the cost model. The data is very big, so it's distributed. In this case, I'm showing it split across 4 JVMs. It's split sort of vertically in this pattern. It's kept in the Java heap, not off heap. The data, we let GC do the right things. Because of the way we structure the data, the standard default old school collector does a very good job. We happily run with 200 gigabyte Java heaps, and they have modest 1-2 second pauses occasionally. 10 gigabyte heaps, I do on my laptop all the time. They're cheap and fast. They just work great. It's not just one vector, of course. It's a two-dimensional table. And going across, there's some collection of column types that represent some real-world thing that you're trying to track. In this case, maybe I'm collecting information about people who are going to drive cars and how many they have and what age they are and whether they're male or female and things like that. And this is similar to an R data frame for people doing data science. Really, the top-level frame is simply a collection of pointers. It's an array of vectors. And I can add and subtract vectors freely. I can shuffle them and reorder them any way I want. That's all cheap and free because it's just a pointer change to do that. The vectors are aligned in memory so that when I go across, I don't have to change JVMs to get all the different values in that struct going across with that single observation. And that's key because it lets me have a known cost model for visiting all the columns of any particular observation. Within a column, the data is chunked. Chunk is typically 1,000 to 1,000,000 elements in length. It's a unit of my compression strategy. There's about 20 different compression strategies in use here. We'll take a look at that chunk of data and think of an appropriate compression strategy. The strategy lets me do a get or an add or set in a few clock cycles. So the guarantee is I can always pull the data out in a handful of clock cycles and get the real value. And that's key because I'm going to pull it in memory through the cache hierarchy into CPU registers, still compressed. I'm going to decompress it just exactly when I use it, and then throw it away. I'll never store the decompressed version anytime in memory or in caches. It's only in the registers. And that's because the compression saves me on memory bandwidth, and that is in fact typically the bottleneck that we have running with the big data. So we can actually outrun, say, BLAS regimes who are storing full width doubles if the data set happens to represent small ints or Boolean values that are shown as a bit vector, because we'll just compress and we'll let on memory bandwidth. Okay, I think I mentioned this already. Within a collection of chunks like that, all the items are all accessible in the same JV heap, and they're typically accessed by a single CPU as a single threaded operation on that row. The core that's doing the work can read and write these things in any order. They're all mutable. It's full Java speed all the way down the line. And of course, this is my unit of parallel execution. One core will grab a chunk of rows and do a pile of work with it. And that's a big enough piece of work that it covers the overhead costs of launching a fork join task, of launching a thread as needed. But it's small enough I get good fine-grained data parallelism. So that the sort of standard thing is you'll have several hundred chunks to maybe a million chunks on a node, and you get quite good data fine-grained parallelism out of it that way. And then the code that gets written is this very simple MapReduce stuff I'll show you in a minute. But of course, it's not just one core. All the cores light up and grab and go all at once. So sort of a typical operation is you fire up some job, all the cores jump in the data, they all make a big parallel sweep through it. Fork join is handling the load balancing within the system. H2O is handling load balancing across systems. It handles all the communication and the data management issues that come with that. And the end result is you get some computation done at memory bandwidth speeds, many gigabytes a second kind of rates. So there's a taxonomy, a frame, which is a top-level two-dimensional structure that you can freely add, subtract, and reorganize vectors. Vectors are metadata representing a collection of chunks of data. The vector spans JVMs, it's distributed, whereas a chunk does not. A chunk is within one JVM heap. The chunk's collection of maybe 1,000 to 1 million elements kind of varies. Each element is conceptually a job of double, but how it's actually represented in memory varies according to compression strategy. And then if you go across instead of down, it's a row. And it's just all the elements. So that's the way to think about how the data is presented. It's the programmer's model for looking at the data. So let me talk about how we run through the data with code, and then we'll look at some of the code examples here. So the standard workhorse, it's not the only parallelism, but the most common one, is this MapReduce paradigm. It's a map from type A to type B, where the type A is typically your big data input. Millions, billions, trillions of rows of data. And your output is either big data or it's small data, Hojo being plain old Java object for the non-Java programmers. It's just a struct. And you can have both, big and small outputs. And then the reduction is you're going to take two type Bs and reduce them together. It's a standard aggregate roll-up summing kind of thing. The general programming paradigm then is you extend an instance of MapReduce task, override the MapReduce call with your own favorite flavors. You make a new instance of this thing, say do all, and you get your result right back in the instance you just made. And so let's go look at that example. So here we have a neighborhood cluster. I'm going to say new Mr. Task at the top, do all data. At the time I say new, some JVM who's running the show here has an instance of a Java object. In blue in the lower left there. When he starts executing the do all, he says, wait a second, I got a job on all this data, I don't have it all local, I need to send the code to the data. So he makes a copy in a logarithmic tree fan out, hands a copy to his two friends, who hand a copy to their two friends, until everyone has a copy of it. So logarithmic to the depth of the cluster, everyone gets a copy of the top level instance of the Mr. Task object, which carries your code. Within a single node, then, we switch over to using Dudley's fork join, which is a classic divide and conquer type of approach. Top level task says I have all this data on this node, it's more chunks than I have tasks available, so I'll go ahead and clone myself and say you're responsible for the other half, and we keep doing the divide and conquer until we have a separate task for every chunk of data in the node. And once that happens, we start executing. And the execution is whatever that map call does, it converts that task object to the B flavor, gives you the output result for just that chunk of data. And once that's done with all the chunks, actually pair by pair, as the maps get done, reductions happen. So we don't do all the maps followed by the reduction, which is common in the Hadoop world. Every time two maps are done, immediately reduction happens. When another two maps are done, reduction, and then reduce again, and so on. So the reductions are eager and happen on the fly as you roll through until you end up with the reduced result in some top-level instance on a node. And then you go back and do the reductions back up to log tree in reverse, where people at the leaves have computed a result, they send it back over the wire to their parent in the tree, who does a reduction, and then the reductions roll up the tree node by node until the last reduction pushes the final result in the top level, and that's the output. That new Mr. Task.doAll can launch, go through the cluster, and come back typically in 10 to 100 milliseconds, like really fast. So if you have more data and fewer cores, it's going to take longer. Kind of depends on the ratios. But if you're looking at gigabytes of data, you can expect this to be done in low millisecond counts. So variations will depend on your speed of your network and things like that, but it's a really fast operation. Okay, so let's look at the kinds of things we can do with the MapReduce, just a quick flavor, because it is such a workhorse in the system. So here is an example from linear regression, just the sum of squares here. It's really easy, right? So type A here is a double, type B is also a double. They don't have to be the same, in this case they are. And the map is just square it, and the reduction is just add the two type B's and return type B. And I can write these 5 lines of code, and I'll get something that will run every download speeds across a terabyte, and just like that. So I have a more complicated operation. Here I've got a set of fields I want to do. I'm going to compute a bunch of sums and a sum of squares. In this case, my type A is the pair x and y. My type B is the this pointer of the Java object, the linear regression pass number 1. And that's kind of key because the this pointer can get pretty darn complicated and hold lots and lots of interesting stuff. And as an efficiency hack, I ask the programmers to write a for loop over an array. In this case, the chunk is your array. And you write a for loop over a chunk of data. So here, instead of getting an x, y, I have a chunk of x and a chunk of y. And these are carefully aligned, so they're all the same length, and they're all the same JVM, and they're all next to each other. And then there's a simple for loop. Then there's a chunk at, and a chunk y at, and an x at. That's the decompression step. Same semantics as an array load, but under the hood, it typically does some sort of bit extract or a shift scale add, something to be done in a couple clock cycles to decompress. And then you have the rest of your math as before. That model right there is the standard workhorse for doing all kinds of stuff. So here's an example of doing a filter. I'm just going to find all the people who pass my filter, all the young male drivers in my data set, because these are the people I'm going to have insurance issues and accident issues with. So I just have some simple tests, and I got some interesting collection of people pass the filter. I can accumulate them. I can write the people who pass that filter by appending them into an empty set. So at the bottom, I make a new empty appendable vec. I call my do all on this filter object, and what I get back is a big data output set, which might be much bigger than it fits on one node. If I start with a trillion and I have a 99% filter, I end up with something on the order of a trillion still. So it's just not going to fit on one node. So the output is distributed as well. It's kept ordered and executed entirely in parallel while you're keeping order. But you end up with a distributed set you can now go on to your next step with, however your filter is doing there. This example is simply going to show you what it means to write single-threaded code that is going to do something more interesting. I have some array that's going to collect people. I'm doing a histogram. In the map call, I said new. Make me a new long, two-dimensional array of longs. I make an array in a map call. Well, how many maps do I run? Okay, well, I run maybe 100, maybe 1,000, maybe a million on a single node. I've got 10, 100, 1,000 of these car ages arrays floating around. Now, it's private to this map, because it said new right in the map call. So that plus plus operator, doesn't have to be atomic. That's a standard non-atomic x86 add one to memory operator. So because it's not atomic, it's not very safe. But it's single-threaded code because it's on a private data set. It doesn't have to be very safe. So this is just standard single-threaded code. And I end up with a distributed set of my car ages arrays. So because they're one for map, I do have to do the reduction now. And that's where you get the concurrent sums happening back in here. I have utilities to help with that. That's just the standard Saxby-Daxby style loop there. Walk through arrays and add them element by element. All the concurrency controls handled by H2O and for join, and you don't have to think about it at all. So here's one that's a little bit different. This is going to find uniques of a data set that's distributed. Here I'm saying new in the constructor instead of new in the map call. And that means that I'm going to have an object which is initialized with the time I said new and pass on the cluster for everyone to look at. The map itself adds in parallel to the same instance of the hash set as every other map on the same node. So there's one of these hash sets per node, not one per map. So the maps are all sharing. So that hash set has to be concurrent safe. So I pick non-blocking hash set to be concurrent safe. However, I still have to have a reduction here because I do have separate nodes that are accumulating results. So there's a map that's on one node is collect all your uniques, and a reduction is bringing them together as they cross the wire and roll that log tree. And then, you know, whatever, 6 or 7 lines of code, I found uniques across a cluster set. Okay, just thought through this already. Because it's in the init call, it's typically an init-only field and shared. This one's written, so it has to be reduced and has to be concurrent. Okay, let's talk about the limitations here. The code is going to run distributed, which means you can't really do any machine resource allocation or I/O because the system out print line is going to appear on one node and not on everything or not on the cluster as a notion. Right? No new threads, no locks, no system exit. No global or static variables because they don't become cluster global, they stay as no globals. And so instead, there's other ways to think about global data. Small global data in which you read, you just put in your constructor, that will be shallow copied around the cluster for everyone to read and use. Small global writable state has to be done through the reduction mechanism. You have to have some way to say, I've written something, piece of here, some piece of there, I have to fold these together, and that's what reductions for. The mid state goes into the read and writable distributed vectors. So you can have output as either small or large, and you handle it a little bit differently. And then the whole notion of the map reducing is you make a pass of the data and get some result back, and you make another pass, another pass. It's called both synchronous parallels, the coding paradigm here. The strengths of this thing are interesting though. The code runs distributed in parallel essentially without effort. Millions and billions, trillions of rows, thousands of cores. You write in a single-threaded coding style. There's no concurrency issues. There's no knobs needed for the GC or the CPUs or network. You get really good data placement, get really good load balancing of cores and CPUs and the like. There's no hot blocks, no hot locks. Here's an example of k-means. So it's an eye chart. I hope nobody can read it. But somewhere buried in there, there's a constructor filling in some fields, there's an input output, there's a reduction call that's doing a radials add and all kinds of arrays. There's a map call which starts with new, a bunch of arrays. There's a giant for loop that's finding nearest members in the cluster and doing all kinds of math on it. And really the takeaway here is that in the system there's 250 or more instances of Mr. Task with tens of thousands of lines of code. It's mathematicians writing math, and H2O running it at scale. So I'm the tool guy. I'm making a platform that is being used by mathematicians all over the world to write interesting high-end, high-level math and have it run at scale. So this is like, there's something going right here that people can sit down and write so much lines of code and have it be parallelizable and do so much good stuff with it. Okay. So let's take a look at the block architecture. I'm going to break it down a little bit. There's, I guess it's purple now. It's red on my screen. There's a cluster building block in the lower right, which is sort of the base core and JVMs. There's a notion of big data. There's some big code. And then the side in blue, there's external clients. And I'll break it down each one of these in turn. At the base layer, we have an H2O node object, which is a proxy for local resources, your CPUs, your memory, your disk. There's a serialization layer. I'll talk about that in a second. There's these fork joins, a fabulous, very lightweight mechanism for handling very fine-grained computations on node. Auto buffer does all things I/O. In particular, it transparently flips between TCP and UDP communications as according to the size of the data structure being passed around, or it does disk I/O and/or an I/O style channel. There's a reliable remote procedure call layer. It's reliable because we use UDP, but it has to be reliable anyhow because we can make TCP fail, because we can trigger a Linux distributed denial of service attack and have TCP drop connections on us. So we have to have a reliable RPC for TCP connection, which means you can pull a cable on a cluster and wait 5 minutes and plug back in and it'll all just work. Keys and values goes into the key store. I'll talk about that a bunch more. But these are where we're holding on to the big data and serialized Java objects for all kinds of things. So I mentioned the serializers, the Weaver, yet another Java serializer, really. If you go look on the web, you can find all kinds of studies on speed, performance, and the issues about different kinds of serializers. This one handles cycle-free data only. The schema is unknown in advance. The first time we see something we have to serialize we haven't seen before, there's a code generated for it, and there's a handshake around the cluster to describe the schema for that particular class. And then thereafter, there's a tiny type ID used to identify the class and all future communications on the cluster. So what really happens is that after that first hit, the overhead comes down to 2 bytes, and then the object just streamed out immediately thereafter. There's a lot of compression going on, especially on large arrays. It's very common for people to oversize arrays because they don't know how much data to hold in there, and the tail has all nulls. There's some prefix that's full, and it turns out that we might get suffixes null, and it turns out that the array might be defined as long, so full of values that aren't very big. So there's a lot of ways you can compress the data. We're fast with this compression as well because of the code gen involved. It's literally read a field, write a byte into an I/O network buffer. It's entirely memory bandwidth bound. I've looked at the numbers. We're easily 10x faster than the fastest other serializers I can find out there. It's like stupidly fast, given the limits of cycle-free data. Okay, let's look at the yellow stuff. There's a distributed key value store built off the values in a remote procedure call. I'll talk about that more in a minute. It's pretty exciting though because it gives you the Java memory model with exact consistency and speed. It's fully caching always. Caching gets are about 150 nanoseconds. It's a lookup in a hash table, and that's it. You're done. Puts can stream at network bandwidth as opposed to network latency and still preserve the exact consistency semantics. There's transaction support as well. Built over that, we take the values, some of which are holding all kinds of exciting things you build in, but some of those hold big data. So the chunks live as a value object, including all the compression on chunking, and then collections of chunks make a vector, and frames are built over that, and as you're distributing big data. So back to my architecture slide, the green stuff. This is distributed fork join, which at its base layer starts with Douglas fork join, uses a reliable remote procedure call to distribute code around the cluster, and from there we build up the MapReduce workhorse. So MapReduce is not the only programming paradigm we do, but it's by far the most common one. And then from there, we build up the algorithms, the sort of the star of the show, deep learning, neural nets, random forest, gradient boosted method, generalized linear modeling, which would be logistic regression is the main use of that. All kinds of exciting algorithms are built up there based on that workhorse. On the external client side of things here, there's a web server built in. Has a well-defined, well-spec'd API for doing all kinds of machine learning and data lunging tasks. Built in there as well is a thing we call Rapids, which is essentially a list evaluator, which will encode into URLs, and it's fully first-class functional. You can do anything with the functions, and particularly you pass over maps to the big data, and that feeds into the R and Python clients. So you can sit down at your standard R session or your standard Python session and write some Python code that would do something sensible in Python, and then just flip the data set to be an H2O frame instead of a standard Python object, and instead now runs on a cluster. And what you might be doing in gigabytes on your laptop in Python, you go to terabytes in the cluster sort of fairly directly. The R integration is actually substantially tighter. It's almost drop in and go of code that's running in your R client will just up and run on the H2O cluster. There's a web interface called Flow, which is got a really nice GUI interface for people who are wanting to click through machine learning tasks without having to learn how to program or R or Python. There's an interesting audience that likes to do that kind of stuff. So that's a top level H2O architecture, and I've talked fast for 3 minutes. So I'm going to stop for a second and see if people are comfortable where we're at, and I'm going to look at a deeper dive in distributed key value store. So this is like, if you space a question right now on what we've seen so far, this is a good time to go ask it. Yeah, the microphone's coming. I need to surprise the microphone guy.
Oh, repeat.
Yeah. Oh, that's okay. If you shout it, I'll repeat this question, but maybe another one after it.
So, distribute data that's multiple nodes. So, maybe you'll mention that.
Okay, so we distribute the data across the cluster. What happens if you lose a node? And the answer is, we decided to not mess with HA, high availability. We started out that way. That market is well served by other people. We're not an HA cluster. We're a giant calculator. So if you lose a node, you lose the cluster. That said, I can reboot a cluster in seconds. And the data load times are almost always disk bandwidth bound, where you can totally eat whatever your disk size is. All spindles will light up and will suck the data in parallel on a Hadoop cluster or S3 or anything like that. So that 7 terabyte data set I loaded in, that took a couple minutes on S3. So it's fast.
Okay, thank you. I noticed when I want to do one other, your greedy reduction algorithm, does that pose any problems for the types of aggregations you can do?
Say that again, I didn't catch it all that.
You're using greedy reduction, so as soon
Yes.
as there's a data set you can use, but that poses some limitations in the kind of aggregations you can do. Does it not?
So it does. The aggregations have to be, well, it does, but it's not as limiting as you might think. The reductions are actually almost, they're done in order. The order of the maps is statistically through the code in linear order, so the reductions are actually truly ordered. So in that sense, it's as if you do reductions one after another. And in practice, they're almost always executed in order. Sometimes you do get out of order, and then you'll have some reductions wait until the appropriate map finishes.
Thank you.
Hello. I had a glimpse about data mining algorithms in your slide, and I was thinking about these algorithms must be aware of the structure of H2O, or can we reuse the libraries written in Java, like for example Wake and stuff?
Okay, so the algorithms we're using are all written knowing about H2O. So internally, the implementations for deep learning and the like, that knows how to say at and set instead of using some sort of array syntax. It uses the limitations that are built into the model. So in particular, I'm not taking somebody else's writing code and make it run distributed. I don't take Fortran libraries and distribute them and have them run in parallel and do that kind of thing. So it really, they're from scratch implementations.
Thank you very much.
I'm not seeing them right now, so I'm going to roll on. And then we'll have another QA session here at the end. Okay, so I have a KV store. It has some interesting properties. We use it for doing the obvious cross-node communication, where you're going to put the key and value in one node, and some other node, you're going to say get a key and you'll get a value. I'm going to follow the Java memory model. And keys are used externally to point to data sets and models results. And something in Python, I'll have some data set, I'll give it a name. And that'll be the name that's being used in the cluster to belong to that data set, even if it's distributed around the cluster. Maybe some models that build, there's all kinds of temporary results being made. Internally, every kind of the temporary data set structure, all kinds of control logic, as well as the big data go into the key value store. So it's a heavily used key value store. It's a hardware-style cache coherency protocol. Everything can be cached locally. Cache hidden gets taking, as I mentioned, about 150 nanoseconds to do a hash table lookup. Puts to different keys can overlap. And in particular, it's a very common case of our writing a lot of attempts that I'm going to flood the system with writes to unrelated keys because I'm filling in all chunks of a large temporary vector. And those can all completely overlap and still follow the Java memory model, or not, according to whether I want to be volatile or non-volatile access. Puts always do network bandwidth limitations. It's not latency. I don't have to wait for some sort of ACK back to say that the receiver got it. I can just fire and forget the data, and the ACK will come back later. Locally, a put, same as a cache hit. It's 150 nanoseconds. So I'm putting data that's going to be home from the local node. The one restriction here is puts to the same key from the same node have to order. And that turns into a network latency issue. I can't send the next write to the same key from the same node until I get a reply back that that write, the first one I settled out. Keys are randomly placed on a cluster or pseudo-randomly placed, which gives me good average behavior. I don't get hot block kind of issues, except locally, individually, onesies and twosies. You don't get a whole section of hot issues. Okay, so I mentioned that keys have a home node. They're pseudo-randomly placed. The system itself is fully peer-to-peer. There's no master anywhere. There's no master for the keys. But I can look at a key by inspection, by the hash function, and know where its home is. The home is responsible for breaking ties on racing writes. And it does atomically execute transactions. And it's the ultimate truth for gets. And that's really the only purpose home has. It's not doing any other, it's not doing any sort of other delegation going on. Values, however, do track coherency, sorry. The values have a set of what other nodes are sharing a value, a copy of it. And when the value changes, that list of who else has a copy is used to issue invalidates. It's very similar to a distributed cache coherency protocol in hardware cluster. And that will also force write ordering from same key, same node to the home for that guy. And so to make it work, values hold a reader-writer block. It's a simple, small counter that has to be atomically up and down. It's the count of outstanding gets. I'll show you an example here in a minute. Or there's a put in progress, and this value is about to be replaced with a new value. And it also has a concurrent bit set of what nodes are being cached. Okay, so let's go look at an example here. And then I'm going to claim I'm out of wasting out of time. So imagine I have a 4-node cluster holding a single key, K1. Node A is holding some value, V1. And it's quiescent, there's no gets in flight, so you can't hardly see it. But node A has value 1 and a 0 count of gets in flight, and it's caching on node A. That's what the little syntax down here is. It's actually a 4-node cluster. The other nodes don't hold anything yet in this little example. So now what I'm going to do is decide an eye chart. Node B does a get, and he wants to get a copy of it. So he fires off a request because it's not in his local cache. So A says it gets in progress and raises his count by 1. He adds B to the list of people caching it. He sends back B1 to B, who puts it in his local KV store, and the ACK back. But as soon as he gets a copy, he can continue execution. The ACK goes in the background. The ACK comes back, lowers the count of gets in progress to 0, and B now has a copy of the thing on node A. If C and D do the same thing happens, although they're all overlapping in this example. C request, D request, the count goes up, the cache gets bigger, results come back, and then the ACK unwind the count. At this point, at the end of here, everyone has a copy, it's fully cached. Everyone can just grab the copy at the standard hash table lookup cost. You don't have to wait for the ACK to complete, you just have to get your data and you're good to go. So given a fully cached situation here, what happens in some issues with writes? Okay, now it gets complicated. So welcome to cache coherency protocols 101. Node C is going to write put a value 2, replace value 1. So the cache of the put is a local update. So he just updates himself locally immediately, and that is valid in the Java semantic model. But he sends the update to the home node for key one, which is A. And so A ends up having to do an atomic update to replace value 2 for value 1. There might be racing threads who's still finding value 1 at this point, so the put isn't yet atomically available, not completed. A then locks value 1, saying no more nodes can cache it. At that point, he knows that only B and D have copies of it, and he needs to go clean them out, invalidate them. So he begins issuing invalidates to B and D. When those acts comes back from invalidates, he knows that no one else in the cluster has a copy of the old value 1. At that point, the value 2 is now semantically available to everyone. The put has completed. This is the visibility. You only find value 2 at this point. So he then sends his act back to C. So C knows it, and at this point, C has the semantic equivalent of a volatile store has happened. And at this point, C can carry on with other operations, knowing full well that if anyone asks for K1, they'll get the value that C just wrote. In particular, it means that C can update something that he wants other people to see and update a pointer to it as 2 separate steps. And if somebody fetches the pointer that C wrote, they will guarantee fetch the value that went before it. It's the standard backwards and forward relationship you have to have in Java volatiles. And you get it using the protocol this way. Dang it. Okay, so let me go back one slide here real quick. So key things to look at this are parallel bulk reads always cache locally and have no other coherency. And once the value's been cached locally, it costs you nothing to read a value again from the cache. Parallel bulk writes go at network bandwidth rates, not network latency rates. You can string them out in parallel across the network. It's the only back-to-back bits and puts on the same key that start seeing the invalidates and have to take latency bits. And only if you care about the ordering, if only you're doing volatile stop puts, if you need to have that level of order. So the major operations that we see being done in the cluster always go at the maximum possible speed allowed by the hardware in question. There are only a handful of cases where we actually see the invalidates causing things to slow down. Okay, so I'm going to wrap it up here. What is H2O? It's clustered memory computing. It's clustered data, column or compressed. It's fine-grained data parallelism via MapReduce, where you write single-threaded code, have it run parallel distributed, like really well. It's a high-speed, exact consistency Java memory model to help developers write all kinds of exciting code. Highly integrated into R, Python, Scala, Spark, Java, web interface. It's best for machine learning algorithms, done distributed. It's like a real tool builder's delight platform to mess with. So, we're making math scale. If you're interested in working on H2O, you can go to this website or poke us in general at H2O, the support email, and somebody will talk to you about what kind of stuff's going on and what we're looking for. So that's it.
All right, thank you. So if there are questions, please raise your hand, please.
Hello. Two questions. The first one really quick. Which JVM do you use? Do you use Hotspot or some more exotic JVM like Zing that you know very well?
We run on Hotspot, standard, Java 6, 7, 8.
Okay. And the second question is, H2O does MapReduce very fast, and you mentioned in the limitation that not all problems are suitable for MapReduce. You mentioned BSP, and I wanted to ask you if this was a decision that you made after looking at all, let's say, economical problem that people run and say, okay, MapReduce is what people need, and I'm going to focus on that because other problems are not probably ready.
Right, so we stared at the different kinds of programming paradigms out of the box. But we also looked at sort of the business proposition here. And we started out life as a high-performance e-value store with HA and replication, all that kind of stuff. And that market's well served. And after like 6 months in, we pivoted to doing machine learning, which then got us into looking at big data. So then we suddenly had a realm of square data, two-dimensional big tables, and obvious data parallelism. So at that point, while there are a number of paradigms that will work on that, MapReduce works. It's particularly easy to code to. So what we wanted was a programming paradigm. There's a fact that we did next. Start. So what we wanted was a paradigm that we could guarantee good performance in, which was also easy to use. So we had this tension between it's easy enough to write code in, but the code will run fast. Right? And so it's no good to have giant data and code run slow. You're dead. Right? I got 30 rows, I write a for loop, I just want to trillion, it's never going to get done. So it has to be parallelizable, it has to be easy to write to, and the MapReduce sort of fit that bill. Now, having said that, that's not the only paradigm that we use internally or for others. That is by far the larger workload.
What license is your code?
Apache V2. Thank you.
Another question?
How do I store data? Just went over that. Go back. Back. Oh, wait, no. Yeah, there we go. Oops, overshot. So the data is kept, parallel around the cluster in the JVM, right? So it's distributed all over the heap. It's chunked. Where each chunk's holding on to thousands of million elements, and they're grouped carefully aligned in the JVM so that any given row or observation is all in one heap's memory. So one core can go crossways at full memory bandwidth speeds.
Yeah, question. Our data science person said we're going to use this. We have random quantile forests.
We have random forests.
Quantile?
Not random quantile forests. But you're welcome to do some implementation there. We'll take pull requests.
Maybe lost. If you look at recently released deep learning frameworks, then they're actually treating the code that you write symbolically. So they're not executing the code that you write, but they're looking at the code that you wrote and rewriting it so that they can do, for example, automatic factorization and faster computation. Is that relevant here, or is it not really?
So you're talking about automatic rewriting of the inner loops and deep learning algorithms? Yeah, okay. So we did the hand vectorization of inner loops of our code already. There's nothing more to be had. We're hitting the complete upper limit of an x86 processor for doing floating point math. So the more interesting one is GPU versus x86 cores, right? So GPUs are much faster than x86, and deep learning in particular is floating point and flop bound. So there's a trade-off between how big the data set gets before you have enough cores that you can beat the GPU. And so if the GPU's got 16 gigs on the GPU, that says a certain volume of data to the bottom of the GPU, and it doesn't fit anymore, and you can't run them in one GPU. And then people beginning to work on the multiple GPU implementations, but we're sort of well ahead of the distributed version of that, because you can all kinds of exciting problems. You're training the data on the machines, the models drift apart from each other, and they have to be constantly reintegrated. And that's something we've gotten figured out now fairly well. That said, because we're also running Java, we got to do all the bells and whistles to help the model with stability, and there's momentum, and there's added delta, and 1,000 other things in there to make that deep learning thing go well. So we're actually fairly competitive with GPUs at a modest scale, of course, because it's a better algorithm.
So thank you very much for this very nice. A little service.